Okay, let's, you can go ahead and go on. So I think I mentioned yesterday about welding and some of the history. Here is the woodcut that I was sort of talking about that shows arc welding, carbon arc welding in the late 1800s, this I think is in France. And there's a bank of batteries here because they didn't have Edison and Westinghouse to give them wall plug power. And there's some people arc welding here, but they had a big bank of batteries. That's their welding power supply, okay, for welding back in those days, so far as that goes. So, any questions from yesterday, which was just sort of an introductory lecture? Okay, today, I guess I didn't mention that in general, I started to talk about one of the problems with welding is there's not very many people in this country who are actually educated in welding. Okay, the Ohio State, LeTourneau, and maybe Ferris State will graduate welding engineers, and so we turn out 50, 60 welding engineers a year in this country. At the Patton Institute in the Soviet Union, they turn out 5,000 a year. Okay, so they have people who are better trained in that sense, but I was talking about whether a welding engineer is really a discipline. It's not really a discipline. You're better off to learn mechanical engineering or electrical engineering or structural engineering and then apply those things to the problems of welding, so far as that goes. The last thing is the ability to join something limits our ability to use the material. Okay, we talk about all these fancy new materials, rapidly solidified metals, nanotechnology, fine ceramics, well, or composite materials. Well, we just can't join them very well, and we can't repair them. Repairability is a big question with a lot of these fancy composites and stuff. In fact, remember the American Airlines flight was taken off out of one of the New York airports and crashed into Brooklyn or Bronx or wherever it was, and it was the tail fell off because of wind shear or whatever, because they were following too close to the plane that had taken off before them or whatever. And there's a big fight about American Airlines, whether it was pilot error or whether it was structurally deficient repair, but it was a composite empennage, which is the tail of the aircraft. And they had a defect and they repaired it. And one side said, well, the problem was the repair wasn't strong enough. And the other side says, oh no, it's pilot error. He never should have been flying in that type of cross wind or turbulence because of the other takeoff. Well, whatever it was, doesn't really matter. It's very difficult in composites to make a repair that is equal to all the advantageous properties of the composites that you started with. And I remember back in the mid to late 80s when Millard Firebaugh, you might know who Millard Firebaugh was? I don't know. Okay. Millard was a 13A grad, which is the predecessor to 2N. And in the mid 80s, he was Captain Millard Firebaugh, and he was the designer of the Seawolf submarine. Okay, and they were designing the Seawolf, and actually maybe early 80s. He actually came through the program, and he was a top student, so back then they let people stay sometimes to do a PhD, so he became Dr. Millard Firebaugh, graduate of MIT, and he went on to design the Seawolf. Well, there was this big hullabaloo about the alpha sub and titanium subs, and so Congress decided, in their wisdom, to zero the $100 million budget in the mid-80s for the design of the Seawolf. And that's when I first met Millard, Captain Firebaugh. And so he was trying to recover the money to keep the major attack sub program going. And they finally went up to Congress and convinced them that, and Congress finally decided, okay, well, we'll give you back your $100 million, but we're going to give $100 million to the Defense Advanced Research Projects Agency to design a leapfrog technology submarine. The Soviets have leapfrogged us, built a titanium submarine, all we've got is steel, and we need a leapfrog technology to leapfrog the Soviets. So I was invited to a 3-day workshop in Reston, Virginia, and it was very interesting. On the first day, they kind of gave us an overview of submarine design, and they brought in all these aerospace people and things like that, fancy composites and titanium, and they put some of us dinosaurs, the people who knew about welding of titanium, they put us in kind of ho-ho, you know, you're the old technology, okay? Titanium metals, right? And then they had these other people who were going to do the composites. And on the first day, they showed a picture, I think it was the Patrick Henry, which was a sub that had been decommissioned. I think they actually turned it into a target vessel, okay? But in any case, after they took everything out of it. But they showed us a picture of it, and it was a patchwork of repair welds where they had cut out different things, different portions. They showed us a picture of what it was at the end of its 30-year life and all the holes that had been cut in it during the history of the sub. And they pointed out, well, when you're doing your design and conceptual design over the next couple of days of what materials we could use, you have to remember we have to be able to get in there to repair things, okay, during ship overhauls, right? Sort of makes sense. So we went off as the group of titanium metals people to look at aluminum and titanium and stuff. And the composites, mostly aerospace guys, they went off. And they came back, and I remember their presentation on the third day. They said, well, we'll just put a hatch wherever we need it to be in the composite. Because they knew they couldn't repair the composite, okay, if you had to cut it. And so they're just going to put a hatch in there. And I thought, well, they must think a submarine is sort of like the halls of MIT. If you have a great big piece of equipment, you just wheel it out the door and take it down the hallway, right? So anyway, it's a little bit of a ship. You don't have that much extra space, okay, to be wheeling things down the hallway, particularly if they're the size of a small house. But anyway, that's the reality of our aerospace gurus, so far as that goes. Anyway, so the ability to join or repair materials limits the usefulness of the material. And by the way, we still have not built a composite submarine. We're still building steel, but that's part of my material selections lectures. But they still want a non-magnetic submarine, okay? So what are they looking at? That's actually part of the material selection lecture too. They're looking at non-magnetic stainless steels. And that's also part of the material selection lectures when you get to those about you go from a material that costs $2 a pound, $4,000 a ton, to if you used the type of stainless steel you need to have corrosion resistance in salt water. Now, if you're going to use your submarines just in the Great Lakes, you could save some money. But you know, if you were just in freshwater, okay. But if you're going to use it in salt water, you're going to a material that instead of $4,000 a ton is going to cost you something like $40,000 a ton. So, okay. At that point, you might as well use titanium, except there are other problems with titanium, but we can get into those if you want. Okay, let's talk about taxonomy for welding processes. And basically, this comes out of the latest edition of the Welding Handbook, 9th edition. It's the 9th edition. Volume 1 in the back. They have a way to look at welding. And you can ask what a weld is, first of all. Okay, so if you want to know what a weld is, who else would you go to other than the American Welding Society, right? The American Welding Society, this is their standard terms and definitions, written mostly by a guy, Howlett Campbell, who's passed away now, but he was a Harvard grad. And he says right there, a weld is a localized coalescence of metals or nonmetals produced either by heating the metals to the welding temperature with or without the application of pressure, or by the application of pressure alone with or without the use of filler metal. Well, that's very helpful. So I broke that down once to understand that. What is a weld? I actually turned this into a full talk, talk and lecture. Okay, I like to take shots at the American Welding Society. So welding definition: it's either a metal or non-metal. Okay, you can use temperature or not. You can use pressure or not, and you can use filler metal or not. So isn't that great? We've now narrowed it down. It's whatever you want, right? Because it either is or it isn't. There's 4 parameters they have in that definition, and you either can use them or not. That's very helpful. Well, turns out that's why they end up with this huge taxonomy of, 15 different types of arc welding, resistance welding, solid state welding, and this goes on for about 10 pages in the welding handbook. This is allied processes, thermal spraying, you don't have to read all this, thermal cutting, oxygen cutting, arc cutting, high energy beam cutting. Some of the charts get to be simple enough you might even be able to understand them. Okay, this is one that says, oh, well, we can look at it as the operation of materials joining. That's what this course is supposed to be about. And the method could be mechanical fastening, joining, or adhesive bonding. But they don't usually, the Welding Society likes to think of just joining. They don't really deal with mechanical fastening. That's sort of Society of Automotive Engineers. And adhesive bonding, I don't know who deals with that. No one really deals with that as a society that I know of. Process category can be fusion welding, where you're melting, solid state welding, where you're not, or brazing or soldering, where it's not the same as a fusion weld, whatever a fusion weld is. If you want to look at just one of those, fusion welding becomes this huge chart: arc, resistance, radiation, conduction, induction, flame, solid reactants. I mean, here's electrical and thermal and chemical energy. I mean, you try to break it down by how you make the weld, and you run into just a huge mess. This is the breakdown for solid state welding, and I counted up once the old welding handbook lists 199 different processes. They have a table that goes on for 4 pages of all the different types of processes. So that's what this course is all about. And I guess I could take you through each one of them, but I don't think that's going to be very worthwhile. Yeah?
What's the difference between soldering and brazing?
There is none.
Okay.
Okay, except it's defined as the temperature. And when we get to soldering and brazing, there actually is a rationale for it. But the American Welding Society defines it as, actually, I guess I could go through the standard terms and definitions. But they define it as soldering occurs below 800 degrees Fahrenheit and brazing occurs above 400 degrees Fahrenheit. The International Institute of Welding uses 425 C, which is very close to 800 degrees Fahrenheit, just by chance. The American Welding Society got there first and chose 800 F, and then they converted to centigrade. There actually is a rationale for it. There are really no filler metals that melt right at that range. I mean, there's kind of a gap in nature of about 100 to 200 degrees, where we don't have filler metals that work at that range. So everything below that has historically been called soldering, and that's because the technology was developed as an invention before anyone understood the science. Brazing is just soldering at a higher temperature, if you want to get down to it. Now, there are some things that because you have higher temperatures, I'm going to go through and say, well, you get different advantages when you're at lower temperatures or higher temperatures. So there are strengths and weaknesses. So you can differentiate them, but in terms of the physical process of flowing a liquid across the surface, they're exactly the same. But we're going to go through that because we're going to go through brazing and soldering. In fact, for the rest of the lectures, we're going to go through today cold welding and probably joining in microelectronics. Cold welding, I'll involve things like friction welding. Most of you get your little video clip of a linear friction weld. So we're going to go through a bunch of the solid state joining processes. We're going to go through adhesive bonding. We're going to go through diffusion bonding, and then we'll get into flames and stuff. And then arc welding is on the videos from last year, or 2 years ago. Okay. So we're going to go through those. But you're going to see in a second, I actually have my own taxonomy of how to figure some of these things out in what I think is a simpler way to think about it. Not by defining the process, which is what most people try to do, It turns out another way it's been used. There's the director of research at the British Welding Institute, I think around 1980, published this book, Peter Holcroft, Welding Process Technology. So he's the Director General of the premier welding institute in the world, and he wrote a book on welding processes, and this is his taxonomy. A little bit of intensity up and he has, I think he comes a little closer to trying to figure out something that makes some sense. He has welding process classification, and he's got this chart that no one, I mean, you don't have to read it. Actually, it is in your handouts if you want a better copy. But he has source of heat down this way and shielding method. Well, the source of the heat, the first one is no heat. Well, that's a source, I guess. And then mechanical heat, and that could be explosive welding or friction welding. We'll talk about thermochemical, electrical resistance, electric arc, or radiant energy. Shielding method is a vacuum, inert gas, a flux, no shielding, or mechanical exclusion. So he actually is getting close to what I prefer to do, and he tries to fill in the boxes. And actually, you could fill in a lot of these empty boxes with some of those 199 processes.
Who is it?
Pardon?
Who did that table?
The guy who did this is Peter Holcroft. He was Director General of the, or no, he was Director of Research at the British Welding Institute. Good guy, knowledgeable guy. But again, you can be like the American Welding Society and try to define the process by how you make the weld, with or without heat, with or without filler metal and all this other mess. Or you can be like Holcroft trying to say, well, what is it I'm trying to do? I have a source of heat that applies melting or not melting. That's sort of getting back to the problem of the American Welding Society. I have a source of shielding. Well, really, if you get down to it, if it weren't for two things, if I were, most solids want to bond. If it weren't for two things, if I put any two objects together, I put this light pen down on the table, it should stick to the table, but for two things. And so the rest of this course that I'm going to lecture for the next number of hours get down to two barriers to welding. Okay, I mentioned to you the other day, welding is the opposite of lubrication science. Lubrication, you're trying to keep things from joining together, and in fact, we do a pretty good job. Most things don't stick together when you just put them in contact with each other. But in fact, welding, we're trying to stick them together, and the two things are surface roughness and surface contamination. Okay? Now, surface roughness becomes fairly obvious if you think about it. We like to think the table looks flat to you, right? But in fact, on a microscopic scale, it's rough, like this foam. So even though it looks flat, and I might think I'm putting two flat surfaces together to get a lot of contact, in fact, on a microscopic scale, an atomic scale, I'm putting two surfaces of rough atoms and other asperities and stuff together, and I get a very small area of contact. And we're going to, a typical contact area, depending on the force that you apply between the two, typical contact area will not be any more than a couple of %. And I'm going to prove to you a little bit later that even if you go to yield of the material and it starts to plastically flow, you still won't get more than about 30% contact area. You're still going to have 2/3 voids when you just squeeze things together until they're yielding. Okay? And that's separate of surface contamination. And so far as surface contamination, people have understood surface contamination for years. This is a book called Fundamentals of Adhesion, published by a bunch of scientists at Xerox Corporation. Why is Xerox interested in adhesion? Toner to the paper. Okay? Their whole business is how to adhere little particles to paper and then bond them together with heat and pressure. Okay? You melt the full polystyrene. What is toner? It's little styrene particles, okay, that have been, they used to be you just added carbon black to them to make them black, but now we have color toner so they have to add colored pigments to them. But basically, they just weld them together. But in the very beginning of this book, that's one thing I don't like about this is you have to keep on changing the exposure. Anyway, when a plate of gold shall be bonded, this is 1200 AD. When a plate of gold shall be bonded to a plate of silver or joined thereto, it is necessary to begin to be aware of three things: of dust, of wind, and of moisture. For if any come between the gold and silver, they may not be joined together. Okay? Contamination was known as something inhibiting bonding back almost 1,000 years ago. I'm sure it was known even before that. Okay? Dirt, it does not help adhesion. It does help lubrication, and in fact, the best lubricants, basically, the whole science of developing lubricants is to figure out what the best dirt is. Okay? We call them lubricants, but you're trying to find the best dirt. Okay? Now, the strength of that bond depends on the type of bonding. And here we get into a little chemistry. How many of you have had chemistry? Somewhere in your undergraduate program, right? Most of you had it in high school, if nothing else. Anybody not even have it in high school? Okay, everybody had it at least in high school. So, if you remember, in chemistry, there were several types of bonding. Anybody remember the types of bonding?
Ionic and covalent.
Ionic, covalent. There are three primary bonding types. You got two of them. Third is metallic. Okay? We'll go through those in a second. But it turns out the inherent strength. Well, what do you think? People actually ask this question after they developed quantum mechanics in the 1920s. In the 1930s and 40s, they actually started asking the question, well, what's the ultimate strength of the material? How strong can a material be? Does anyone have any idea what the strongest material can be? It goes back to the chemical bonds, the strength of the bonds between the atoms. So if you take one of the primary bonds and you say, what's the strength of just pulling two atoms apart, and then you take it over a whole 1 square inch or 1 square centimeter area, anybody know what type of tensile strength you would get? Or what's the strongest material you've ever heard of? Diamond. Okay, that's the hardest material. But very few people have done a tensile test on diamond. Okay, but you're right, they do a compression test. And in compression, actually that's a good answer. I'll shortcut things. If you take that compression hardness test they do on diamond, and diamond is one of the strongest bonds. It's actually carbon-carbon is the second strongest bond after silicon-oxygen. Okay, in terms of a bond energy, common bond energy. Turns out the silicones with the silicon-oxygen background are potentially better, and that's why you can buy these little rubber cooking mats now that are silicones, and they don't melt in the oven at home. Why? Because the silicon-oxygen bonds are actually a little stronger than the carbon-carbon bonds. Okay, but anyway, so that's a good answer. If you calculate that, you get about 3 million psi as an effective tensile strength. And you've heard people say about carbon nanotubes, they'll be strong, millions of psi. And they presented this as if it's something new, right? You read about it in the popular scientific press, right? Ooh, carbon nanotubes are super strong. Well, here's the book I studied mechanics from, Mechanics of Materials, back, actually, here it is right here. Here's the book. Okay, Plastic Deformation of Metals. It has a plastic cover on it because Professor Bever, who taught me the course, came from Germany. He got his PhD, he got an MBA at Harvard Business School, and then he came here and he got a Doctor of Science degree in Metallurgy. But Honeycomb came out with this book in 1968, and Professor Bever, being very Germanic, made us bring our book to class and made us put a plastic cover on it. Okay? He was somewhat of a stickler for lots of things. But anyway, here is whiskers, fibers, and fiber reinforcement. So back in the 1940s, when people did these calculations and they said, oh, theoretically, steel should be 2 million psi. And then to prove it to you, a student once asked me in this class, well, you say it should be 2 million psi. How do we know that? And I said, well, it's based on the surface energy. They said, well, how do you do that calculation? So I went down, and it took me about 15 minutes, and I did the calculation. Same calculation they did in the 1940s. So here's the calculation that calculation proves that if you assume a bond energy of about 2 electron volts, you get about 2 million psi. But back in the 1950s, people took whiskers and measured the strength. A spinel, or a, not spinel, what's a single crystal aluminum oxide? It's not a spinel, but it's a sapphire. Sapphire single crystal has a strength of been measured experimentally as 2.2 million psi. Let's see, these are experimental measurements, okay? Iron, 1.8. Well, I calculated 1.88. Pretty good, huh? Fortuitous, but anyway. Silicon carbide, 3 million psi. Okay? So, asbestos, 850,000. Soda glass, this is what fiberglass is made out of, 500,000 psi for the glass fibers that are in fiberglass. That's why fiberglass works. You got fibers that are almost as strong as these carbon nanotubes could be, and I bet you can make fiberglass cheaper than you can make carbon nanotubes. But we're going to spend billions of dollars studying carbon nanotubes, and what the people with carbon nanotubes, they've done the theoretical calculation, but it turns out the actual strength of these things is not really just determined by the bond energy. It depends on the defects. Remember yesterday I tore a piece of paper with a notch in it and I reduced the strength by a factor of 10? Well, it's the defects in the material that determine the strength. In fact, the guy who used to be head of materials for General Electric aircraft engines, a guy named Bob Sprague, had a lot of great sayings, and in material selection I'd probably give you a couple of them. But actually one of my favorites is, whenever you first hear about the properties of a new material, write it down, because those are the best properties the material will ever have. And his successor, Jim Williams, who's a professor at Ohio State, his corollary is, whenever you first hear about the cost of a new material, write it down, because that's the lowest cost that material will ever have. Okay? Sort of like a development project like the F-35 fighter or whatever. Okay? The prices are always lowest at the beginning, and the properties are always the best at the beginning of any project. Well, so the thing is, the inherent strength of chemical bonds is very high, and in fact, it's fracture mechanics or defects. And Sprague's quote on that is, he says, material scientists think that it's structure that determines properties, whereas metallurgists know that it's defects that determine properties. Whether it's inclusions or cracks or whatever, it's those flaws in the material that determine the strength of the material. If we look at the relative strength of bonds, ionic bonds are typically 1 to 3 electron volts per atom. Covalent are also, and metallic are also in that same range. I'm going to break that down a little bit further for you. But the secondary bonds, hydrogen bonds, are about 10 times less, and van der Waals bonds are even lower. Okay, so it turns out that polymers, why do polymers melt at low temperatures? Polymers melt at low temperatures because they're long chains of primary bonds, covalent bonds, along the carbon backbone. But in fact, they're van der Waals or hydrogen bonds between the spaghetti chains, right? It's like cooked spaghetti all mixed up. A rubber band is a bunch of fibers, or cooked spaghetti, and they're all twisted up, and when you stretch the rubber, they all align up to some point until they're all stretched out, and then they have lots of strength. And in fact, what's Kevlar fiber? Kevlar fiber is nothing more than they take a certain polymer, they put it in concentrated sulfuric acid and extrude it so all the chains are aligned in the fiber direction. And so it has tremendous strength in the fiber direction, doesn't have such great strength in the transverse direction. It has strengths of 500,000 psi or more, stronger than steel, they'll tell you, okay, for Kevlar fibers, but it's only in one direction. It's only in the fiber direction. where you have the primary bonds. In the transverse direction, of course, who pulls sideways on a fiber? Nobody, right? So you can weave it into whatever, right? And make something that's strong. But basically, it's the strength of the bond. So we need, in welding, if we want to make a joint, we need to make bonds. But frankly, for the types of strength levels we need, 1/3 of 3 million psi is 1 million psi. That'd be more than enough for most welds. And 1/10 is 100,000 psi. So we don't really need tremendous bonds as long as we don't have defects. Okay? We don't even have to have primary bonds as far as that goes. Any questions? So, a little surprising to a lot of people to realize how strong things are. Now, if you go back to basic chemistry, the very first couple of days in a chemistry class, they tell you about something that in the 1920s they called the LeonardJones Potential, where you plot the energy of two atoms, these little dots here. Here's the atom at rest, and here's another one that you bring in from some radius, some distance away. And it comes to some equilibrium distance of separation, and there's an energy of attraction and repulsion in here, okay? And it comes in, it finds its equilibrium spacing at the minimum energy. And that's A0, that's the lattice spacing in a crystal, okay? That's the interatomic distance, equilibrium interatomic distance. And the force of attraction, there's an attractive force, lowering of energy as you bring them together. And the force of attraction is just the derivative of the energy. F is dE/dr, right? Remember that from freshman physics? If you had freshman physics. Sophomore physics if you didn't go to MIT, right? That was freshman physics for me. Okay, so there's an attractive force when you're lowering the energy. When the energy goes up, it's a repulsive force. And so the force is negative, and it actually goes up very rapidly, and there's formulas for all this stuff that you can find in books like this book on fundamentals of adhesion. In fact, a lot of the plots I'm going to show you in a second come out of that book on fundamentals of adhesion, like this plot, which is, you have to get to page 90 in that book on fundamentals of adhesion before you get to the plot that I just drew. But this is the force of attraction. This is the force of attraction, this is the energy of attraction. This is just what I just drew for you, flipped over, okay? One on the bottom of the other. Here's the equation, if you were interested. The internal energy, if you're a thermodynamicist, we know the internal energy is usually called given the units of U. If any of you study thermodynamics, there's the internal energy, the enthalpy, the Helmholtz free energy, and the Gibbs free energy. Some of you are nodding and others are just blank, so it's fine, okay? It's just a question of whether it makes sense to you. And here's the internal energy of two atoms coming together in terms of the radius. And there's the attractive force, which is just an electrostatic attraction. Positive and negative charges coming together. If you studied electrostatics, it's just 1 over r squared, okay? Sometimes they call it the r squared attraction of electrical charges. Electrical engineers, they don't worry about atoms, they only count charges, right? So they don't care about it, it's an atom, but atoms have charges, so it's the same formula. Okay, and this is the repulsive, here's the negative, this is positive, there's the negative. So, and actually there's negative out here to show that it's attractive if it's a decrease in energy. So, there's all that. Now, how does that relate to temperature? How does energy relate to temperature? Anybody know how energy relates to temperature? The higher the energy, the more atoms move around, right? The higher the temperature, the more atoms move around, the more energy they have. There is an equivalence that the energy in electron volts is equal to the temperature times the Boltzmann constant. Anyone ever seen KT before? You're an electrical engineer. KT is used all the time when you're studying noise in electrical circuits. And most electrical engineers studying noise know that KT at room temperature is about 300 Kelvin, is equal to 25 millivolts. Okay?
Thermal energy.
Pardon me?
Neutron thermal energy.
Neutron thermal energy. Okay, so you know it from nuclear engineering. It's all basic physics, right? There is an energy temperature equivalence, and it's given by the electron charge times the voltage. This is the Coulomb charge, you know, 1.6 or 6.02 times 10 to the minus 18. Anyway, all I know is that Faraday's constant times the electric charge is equal to Avogadro's number. So 1 mole of electrons carried. Anyway, the Coulomb, 1 Coulomb is like 10 to the 18th electrons, okay? And 100,000 coulombs is equal to Avogadro's number of charges. Boltzmann's constant, Boltzmann was a thermodynamics guy who gave us the beginnings of statistical mechanics, or statistical thermo. But there's an equivalence between voltage and temperature given by E over K, and that says that 1 volt is equal to about 12,000 Kelvin. So 1 volt of energy, and remember a primary bond can be 1 to 3 volts. So what temperature should it take to break primary bonds? It should take 10,000 degrees, but in fact there's a distribution of energy. That's where you get into the Maxwell-Boltzmann distributions. And when melting occurs, it's only the particles with the highest energy that melt, that start the melting. And there's a distribution. They're not all 1 to 3 electron volts, because in statistical thermo there's a distribution, okay, in the Maxwell-Boltzmann distribution. So in fact, metals, the highest melting metals don't melt at 36,000 Kelvin, they melt at 3,000 Kelvin. Tungsten, right? Because it's the top 10% of the energetic atoms in that ensemble of Avogadro's number of atoms that are going to result in the whole thing starting to melt. Okay? So, anyway, so there's a lot of energy in electrical in a chemical bond. This, I'll just show you, this comes out of this Handbook of Adhesion. And the reason I show you this is 1929, P.M. Morse. Who was P.M. Morse? He was a professor of physics at MIT. So he's writing chemistry books, things in 1929. These are some of the early quantum mechanics calculations based on spectroscopy and other things that were done. Well, it's actually where the physics building is now, but the Harrison Spectroscopy Laboratory used to be right outside the window where you get your breakfast. Okay? Now it's a hallway with an ugly floor. Okay? Multicolored floor. But that was the Harrison Spectroscopy Laboratory where some of this data was taken back in the 1920s. Morse wrote a book called Morse and Feshbach. Hermann Feshbach was head of the physics department a couple of years back in the 1980s. Okay, so Morse and Feshbach. So here are the different energy levels in wave numbers. That's only a physicist would describe energy in wave numbers because they're going by Planck's constant, or Planck's constant. E is equal to h nu. But anyway, if you can translate all the different languages of, the physicist speaks one language, a mechanical engineer speaks another language, a civil engineer speaks yet another language. Mechanical engineer stresses sigma, a civil engineer stresses S. They don't know Greek in civil engineering. Anyway, if you actually look at the bond energies, carbon-carbon bonds have an energy of 347 kilojoules per mole. Triple bond carbon has an energy of 800, almost 3 times as much. The most energetic bonds are nitrogen bonds, and they don't have the silicon-oxygen bonds on here. Carbon-nitrogen bonds are also pretty high. But why are a lot of your explosives contain nitrogen? Because nitrogen compounds have some of the highest strength bonds, store more energy in those bonds. The other thing with nitrogen compounds, you can also make them with their own oxygen. And so you actually carry the oxidant with the fuel. The fuel is in the strength of the nitrogen bond, and the oxidizer is the oxygen with the nitrogen. So trinitrotoluene, 3 NO3s. Okay, TNT, right? That's where it all comes from. And that's why you need to analyze at airports for security the nitrogen compounds. Now I had an explosion that occurred in the world's largest ice cream plant in Lamars, Iowa, okay? The refrigeration room for the southern plant was about the size of a football field, okay? They had like 21 of these compressors to compress the ammonia, and they're just all lined up like an old, if you ever saw the pictures of the great big ships before World War I, big ocean liners and stuff, and all the coal-fired boilers and stuff. It's just this row of compressors for compressing nitrogen or ammonia, and they had an explosion, did a lot of damage, and I was bringing back the part. This is about 10, 15 years ago, and I had spent the whole day working with ammonia, and the part had ammonium hydroxide and everything else. And when you leave Sioux City, Iowa, you don't get scanned in Sioux City. You get scanned when you land in Minneapolis, okay, before they put you on a big plane. They figure no one flying out of Sioux City on one of those little planes is going to make it to the World Trade Center or the Pentagon, right? Okay, it's only the big planes that have all the fuel. So, and I was going to miss my flight if they had to do anything, if they detected ammonia compounds on my hands. I've been working with it all day, or on this big metal piece that I was bringing back. And it turns out they did scan it. They pulled me aside and they scanned it through their special little detector, and it turns out it didn't pick up anything. Because afterwards, I was talking to a guy from the physics department at MIT who owns part of the company that makes these detectors. And I said, can they discriminate between ammonium hydroxide and ammonium nitrate? He said yes. So I had lots of ammonia, lots of nitrogen, but it wasn't the right type for those detectors. So you can get through with ammonium hydroxide. Not that it does you any good, but anyway. So far as those chemical bonds, again, out of this same adhesion book, here are your average bond energy versus intermolecular distance for covalent ionic metallic hydrogen bonding down by about a factor of 10, and then van der Waals is way out here, okay? Now this is the distance R. And gee, this doesn't look like metallic's as strong as covalent ionic, does it? Even the area under the curve doesn't look the same, right? So what's the answer to that? I told you they all have 1 to 3 electron volts per atom. This gets into your calculus class. We have a spherical geometry, and so I have to do 4 pi r squared dr and integrate it in order to compare the areas under the curves. I can't just look at that area under the metallic curve and this area under the covalent ionic and say they have the same energy. I have to take the area of the sphere times the little thickness of that sphere and integrate it over 0 to r. And since r goes further out for the metallic bonds, it turns out if you do that, the area under the curve for metallic bonds is greater. But the point here is metallic bonding reaches out further. Typical atomic distance is like 1 nanometer or 1.5 nanometers. It turns out metals reach out several atomic distances. And that actually ends up becoming important when we start talking about surface energy and soldering. So that's one of the reasons I'm giving you that. But you all learned this in chemistry, right? No, you didn't learn this in chemistry. Okay. So, when we're talking about bonding, we're talking about the energy of surfaces. And if you're a thermodynamicist, you can say, okay, well, the energy of the surface is a function of the Gibbs free energy. And the Gibbs free energy is a function in chemical thermodynamics of the temperature, the pressure, and the chemical potential, which we usually call mu. Now, if I think of mechanical energy or pressure and how that relates to bonding, I can draw myself a little one-dimensional graph here in terms of the pressure in megapascals. What's 1 megapascal in psi? Anybody know? 145 psi. So if I only apply between 2 surfaces 145 psi, I'm sort of fixturing pressure, so I'm just kind of holding 2 parts together to put them in a milling machine or something like that, right? To keep them from flying off when I'm milling or drilling or something. Diffusion bonding, I might be up at 14,000 psi or something, okay? If I'm doing cold welding to try to weld things together, I'm going to be up considerably higher. And if I'm doing explosive bonding, which we'll talk about in a second, I could be at 1,000,000 pascals. Okay, probably not quite 1,000,000, maybe 300,000 or something. If I talk about thermal energy, and I actually just made this one up this morning, so it's a little scratchy. Cold welding is done at room temperature. Melting of steel is done at about 1,800 Kelvin, and vaporization of steel is about 3,300 Kelvin. Okay, so you have a lower range, smaller range of temperatures than you do pressures. And chemical potentials really depends on what specific bonds you're dealing with. Okay, so this is all still fairly general. But let's talk now about, get back to these two things that inhibit bonding. What are they?
Roughness of the surface.
And the other is contamination. Okay? So that's going to be a theme. So one of the questions you can ask yourself, let's say I take a piece of chalk and I create a new surface. I just created two new surfaces there. How long does it take to contaminate that surface? How long does it take for a monolayer of atoms to strike that surface? Anybody have an idea? Well, it actually has a name. It's called the Langmuir. Irving Langmuir was a physicist who won the Nobel Prize working at General Electric, studying surfaces. And it turns out that NASA studied surfaces a few years later. Adhesion or cold welding of materials in space environments. This is a 1964 book. It is, when I got to it, you couldn't get it anywhere else, but a symposium presented at a meeting of E21 on space simulation, American Society of Testing Materials, and lubrication fundamentals, okay, of the Aerospace Council, 1967, sorry, okay. So this is a 1967 conference that NASA had been funding research for about 8 or 9 years on adhesion. And why was NASA interested in adhesion? Well, I don't know. Now I know. When they did the first mercury shots, NASA used graphite as a lubricant. And graphite has this crystal structure. You can tell this is graphite because the atoms are black. But the crystal structure of graphite and many good lubricants is what we call hexagonal close pack. The planes, the atoms form plane sheets. Okay? Hexagonal, if you're a chemist, sp2 bonding, okay, hybrid bonding gives me 120-degree angles. But it's sheets of carbon, nanosheets. Oh, sorry. Anyway, nanosheets of carbon. I guess now we have a name for it. Okay. And on Earth, graphite is a very good lubricant. Okay, you squirt it in your locks, you know, in your car, you know, stuff. But it turns out, and they used it on the first couple of Mercury flights, and they found that when they got up there and they were in a vacuum in space, it was no longer a lubricant. Everything was sticking together. What was happening? Well, NASA went out and spent millions of dollars to figure out what was happening. But it turns out that, remember I told you carbon-carbon bonds, if they're not contaminated, can be very strong. And if I just put carbon next to carbon, and it wasn't contaminated, and it didn't have a rough surface, it would stick. And even if it's only sticking 10% of 3 million PSI is still a lot of PSI in terms of something that's supposed to be sliding. Turns out when you get up in space, there's no oxygen around. And it turns out the only reason graphite's a good lubricant on Earth is because the surface, the top surface of these planes, is contaminated with oxygen. The oxygen in the air goes to the surface, some of these planes on the graphite, and now you have a carbon-oxygen bond, and that's a satisfied bond. The surface energy of a carbon-oxygen surface is very low compared to a pure carbon surface. The excess energy, that carbon surface wants to find something that it can grab onto and lower its energy, and oxygen is the perfect thing, except if you got a vacuum, you can pull it off. And that's exactly what happened, is they found that in the vacuum of space, they basically turned their graphite lubricant into an abrasive, and they were having a few problems with some of the knobs and stuff. Okay, wasn't good. The astronauts were not happy. Okay, they studied this, and out of this little book, they have this little handy chart that talks about variation of pressure and related. This is in your handouts too. Of pressure and related quantities with altitude. So the altitude in hundreds of thousands of feet, the apogee of Sputnik 1, okay, pressure in torr down here at 10 to the minus 8 millimeters torr, or millimeters of mercury, depending on which one there is, microns of mercury. Density down here, time to form a monolayer at 25 degrees C. So if I'm at atmospheric pressure, where's that? So sea level, the time to form a monolayer is something on the order of 10 to the minus 8 seconds. Okay? So the Langmuir is 10 to the minus 8 atmosphere seconds. So when I broke that chalk, there were enough molecules in this room to completely cover the surface, those two new surfaces of chalk, within 10 to the minus 8 seconds. So before I even had them apart, as soon as that fracture formed, they're contaminated, unless I'm in an ultra-high vacuum, or in a very clean atmosphere. I had a student, actually he was a 13A student, now a 2N student, Dan Reese, did a master's thesis for me back in the early 80s on welding of titanium. Why was anyone interested in welding of titanium back then? Early 80s, like 1982 or 83. And he was doing gas metal arc welding of titanium. He was doing it in a glove box. And we had the whole thing set up in the glove box. And he was using a little dust buster to clean up inside the glove box, to clean up the glove box, you know, because you get spatter and other stuff while you're welding. And he came to me one day, he says, the dust buster's not working. And I bought 3 of them in the last 2 weeks. And I said, what? And anyway, so we start talking about it, and I realized the carbon brushes on the motor of the dust buster, which work fine in the air with oxygen, he was working in a glove box with 10 to the minus 16 atmospheres of oxygen. It was pure argon. It was 1 atmosphere, but it was not very, the partial pressure of oxygen was like 10 to the minus 16 atmospheres, okay, of oxygen. And all of a sudden, the carbon brushes on that motor had become an abrasive, and it was eating up his motor in minutes of operation. His bus dusters were lasting less than an hour. Okay, so same thing NASA had, but they didn't give me $10 million to study it. Now, what type of lubricant? So what did we do? Well, I said we'll put some molybdenum disulfide on there. Why molybdenum disulfide? Molybdenum disulfide is a high temperature lubricant. Has the exact same crystal structure, hexagonal close packed. But in fact, it has sulfur on the surface. It comes with its own sulfur. Tungsten disulfide, tantalum disulfide, they're all lubricants. But moly disulfide is the least expensive, and it's used as a high temperature lubricant, and the sulfur doesn't evaporate off in vacuums. The molybdenum sulfur bond's much stronger than that chemisorted carbon oxygen bond. So we just contaminated our brushes with a little moly disulfide. We had no problem. We could get an hour or 2 out of a dust buster, right? Okay. So that shows that there is lubrication and welding are really just the opposites of each other. And this monolayer time sort of tells us that we're not going to win the race in time of trying to bond 2 things together if we're at atmospheric pressure. Now, they did do some work even before this. The British, in studying surfaces, I kind of mentioned Rabinowitz's book yesterday in Friction and Wear and Lubrication. Ernie Rabinowitz did his work at Cambridge University in England under Bowden and Tabor. Okay, and if you study anything about surfaces, you find in the 1940s the laboratory of Bowden and Tabor was the laboratory in the world understanding surface chemistries and surface physics. In fact, Ernie Rabinowitz's doctoral thesis used these new radioactive materials. He used tracers, and he would rub soft brass on hard steel, because back in those days everybody thought that what would wear would be the soft material against the hard material, and the hard material would not wear. Because whenever you ran a wear test of a soft material against a hard material, you couldn't detect any wear of the hard material. And so people thought it was the hard material was doing all the wear. Well, Ernie proved the adhesive theory of wear by using radioactive tracers, and he showed the steel was being picked up by the soft brass, but at a ratio proportional to the hardnesses, okay, an inverse ratio to the hardnesses. And if you look at the adhesive wear equation, the hardness is in the denominator, okay? And so steel will be, a hard material like steel or diamond will be worn away by a softer material, but inverse to the hardness. So the harder it is, the lower the wear rate of the hard material. But that's not to say the hard material isn't wearing, because when those atoms come together, there's a certain probability that the steel atoms will go with the brass, or the brass goes with the steel, but the probability has to do with the hardness of the material. It actually is particles of materials, not individual atoms. But in any case, by doing radioactive tracers, Ernie could show that you were picking up a lot more brass on the steel, but you were picking up a fair amount of, a proportionate amount of steel and brass by looking at radioactive tracers. So anyway, and that's sort of a classic experiment. So what are surfaces all about? Let's see how much. We're going to take a break here in a second, but let me just finish up here a little bit on surfaces. If I look at, make up a little model of surfaces. If I have a bunch of atoms and they're all bonded together, these little dashes mean a bond. At the surface, I have no bond. I have unsatisfied bonds. And so carbon dioxide or oxygen or some sort of grease or oil, soap molecule, that's what this is. This is a micelle. It's a soap. It's made up of things like stearates, which have a polar end, and then they have a non-polar backbone, like a piece of spaghetti, if you will, an atomic piece of spaghetti. And it turns out these little micelles will stick on the surfaces, and that's why these unsatisfied bonds on the top surface, this is an unsatisfied bond, have no atoms on them. They want to pick up something to reduce their energy, and they'll pick up anything. They'll do any kind of Van der Waals bond, anything they can, any contaminant that's available, they will latch onto. And so, and the Langmuir tells me that they'll do it very quickly, depending on the gas surrounding them. Yeah.
Going back to titanium, doesn't it have a titanium dioxide surface coating? But when you weld, can you eliminate that, causing it to corrode?
Well, now you're running way ahead of me, but yes, what we're doing here, we have to figure out a way to get rid of the surface contamination that doesn't allow it to reform in the time available.
My question is, why doesn't it reform if you're
It will if you don't put something in between. But
okay.
in titanium, you actually the oxide will dissolve into the titanium at about 900 C. Okay, and the problem with that is titanium is great for the compressor sections of jet engines because it's lightweight and it's strong and corrosion resistant, but they don't put it in the hot sections because if it gets above 900 C and the oxygen diffuses away to the inside because titanium will dissolve its own oxide, you now have free titanium exposed to the air and it catches fire. And they've had several fires in jet engines where some of the titanium in the compressors got above 900 C and you burn up the engine very quickly, like a few seconds, the whole engine goes to powder. Okay, not a good day, not a good day. So there's different things, and the oxide, now aluminum will not dissolve its own oxide. You can heat up aluminum, it melts at 660 C, its oxide doesn't melt until 2000 C, You can actually, supposedly John Wolfe, who was my thesis advisor, used to do experiments where he would resistively heat electrically some aluminum wires until he would melt the aluminum, but the oxide skin, it might have been anodized aluminum that had a thicker oxide skin that was a little stronger. And he could have molten aluminum in the wire suspended and held together by its oxide skin. And then if you supposedly pricked that skin, you get a stream of molten aluminum shoot out. So this whole question on metals, which have very high surface energies. Why do they have high surface energies? Because it's not just the unsatisfied bond from the top surface atom like it is in covalent and ionic. It's from 2 or 3 layers beneath. Metals have extremely high surface energies, and we'll show you that after the break, because it's not just the top monolayer of atoms of the metal, like it is with the covalent solid. It's the top 2 or 3 layers. I've got 2 or 3 times as many unsatisfied bonds in a metal, because remember the metal has a greater distance of bonding. Okay? If you ever studied metals, they talk about clouds of electrons in the metal. Well, those electrons are the bonding electrons, and they reach further than the covalent or ionic electrons, which are essentially tied to an individual nucleus. You know, it's electrostatically attracted to a single atom, a single nucleus. Whereas the metals, hey, these bonding electrons in the metal valence band are free to go, 2 or 3 atom distances away, and you still have this surface energy. So it turns out in metals, I'm going to show you after we take the break, a chart that metals have surface energies 2 to 3 times higher than covalent or ionic solids. And that gets into strength of bonds of the oxides on the surface. How do I get rid of that? My problem right now, I got to get rid of my surface contamination and my roughness. And whether I'm doing adhesive bonding or soldering or brazing or fusion welding, all I'm doing is coming up with a way to get rid of that contamination and get rid of the roughness. If I interpose a liquid, I got rid of the roughness, right? That's why melting, soldering, brazing, melting, I get a liquid that fills the hills and valleys. I don't have to worry about a rough surface if I have a liquid. If I'm doing a solid state weld, I got to break down physically these hills and valleys. Okay? So I got these 200 welding processes, but the way to think about all of them is, at least in the beginning, first cut, is what is that process doing? Or what can I do to get rid of the surface roughness or fill it in with a liquid? And what can I do about that the contamination, which for a metal is usually an oxide, but for covalent materials and other materials it can be other things. Okay? Those are my 2 problems in the rest of my live lectures this semester. How do I solve those problems? But anyway, the Belknap ran into the Kennedy on some maneuvers once, and some of the jet fuel, it was right underneath the elevators on the Kennedy, and some of the jet fuel leaked on top of the Belknap and started a fire. And again, it was the aluminum steel reaction, the thermite reaction. The whole aluminum superstructure caught fire and wiped out the Belknap. Okay, so at the time, the joke in the Navy was a gallon of jet fuel would wipe out any ship in the fleet. And this was not. I think this was either before or after the Falklands. This was 69. This was in the 70s. Anyway. Kennedy was commissioned on September 7th. Anyway, on the night of November 22nd, 75. Okay, obviously my classmate's father had already been relieved to go to a new command by then, so that's why. Anyway, this is a book that actually one of the students in this class pointed out to me once, called Naval Disasters. So if anybody wants to, gives you histories of lots of
21st
things.
century one's already figured that.
It's Naval Disasters, and it's, or How to Lose Your Command in 10 seconds or less. Okay. Okay. Oh, and the question, we'll have class tomorrow, Thursday, no class on Friday. There's been a request to have Fridays off. We'll have class first 3 days of next week, and then you got a class Thursday morning, and then Fridays are off, and then I should finish up by the 22nd. Okay.
Can you
That's
show that
next.
once more?
You do not have class tomorrow?
So it's
We do have.
class on Thursday, tomorrow. Okay. I'm sorry, not tomorrow. No class tomorrow, because tomorrow's Wednesday, and I have something anyway. I would have canceled class if you didn't have your other class. But we'll have class Thursday. So 3 days this week, 3 days next week, and then 21st and 22nd. And then you guys have to figure out whether you're going to borrow videotapes from Jerry, you know, DVDs from Jerry, or watch it off the web, the other 25 hours of lectures, right? Only lecture 1/3, right? So that's that. Any questions? So here's some, this comes out of a book called Adamson, just to give you a little more MIT, actually only sort of MIT history. Physical Chemistries of Surfaces, this is 6th edition. And Arthur Adamson's a professor at UCLA. Alice Gass was a professor at Stanford, and I think she was probably one of Adamson's students. Then she came to MIT as the assistant provost, and now she's president of Lehigh University. But surface tension values, water has a surface tension of about 72 dynes per centimeter, or that's 0.072 joules for those of you that are in SI units, at 20 degrees C, and changes. Organic compounds are all in these tens. The lowest surface energies that you generally find in almost anything are down around 10 per fluoropentane, okay? These are fluorinated, mostly fluorinated compounds, because fluorine has one of the strongest electron acceptors, and so it forms some of the most stable bonds. That's why Teflon and freons and things like that are so inert, okay? Freons are so inert that they basically used to consider them for artificial, as the liquid for artificial blood. It's not toxic, okay? But now we don't use them because they destroy the atmosphere, or the atmosphere's ability to absorb ultraviolet rays. Low boiling substances, well, I mean, liquid helium has the lowest surface energy of anything, okay? But that's at 1 degree Kelvin, so who cares? But it's actually called the superfluid, and you know, because it has such a low surface energy, it has some interesting fluid properties. Here are your salts. Sodium chloride, above its melting temperature, 100, or that should be above its melting temperature, 115, not much more than the water, okay? But the metals that they're showing in here, and being good chemists, they show you the metals that a chemist knows about: mercury, okay, sodium, barium, tin, okay? Well, those are not metals, okay? Real metals are things like steel and iron and stuff. And this is one that should be in your notes somewhere, the handout. But, okay, copper, that's a metal. Platinum, liquid. These things have certain, here's water at 72, remember? Copper, 1500. Silver solid, silver liquid, you know, around 1000. Platinum, 1800. Turns out iron metal is around, if it's very pure, is around 1500. Okay? So the surface energies of metals are 3 times the surface energies, or more, of your ionic and covalent solids. Okay? Why? Because you have more layers of atoms on that surface, or more electrons participating in the whole process. And that extra surface energy of metals is something that's very important when we get to the whole principle of how metals flow in soldering and brazing and displace the fluxes, which are not metallic. And it gets to, why don't we, you can ask the question, well, why don't we braze with ceramic liquids? Well, because they don't have a high enough surface energy. You actually want to braze and solder with something that has a very high surface energy, because those processes, it's actually the surface energies, the capillarity, the surface attraction that's causing the metal to flow in and fill the gaps, okay, and displace part of the contaminants, okay? But we'll get to that. Now, if no questions on that, I want to start talking about cold welding. And you can say, well, why are you going to spend some time on cold welding? Well, it fills up the day. Oh, no. There actually are some good reasons, and not just NASA and graphite and stuff. Cold welding is used a lot more than a lot of people think. In fact, so far as I know, there are probably more cold welds made than there are virtually any other type of weld, because most computer chips have very fine wires, typically gold, sometimes aluminum when they're trying to save money. The wire diameter is typically about 25 microns, 1/1000th of an inch in diameter, and they make a thermocompression bond to the pad of the semiconductor chip, or they make an ultrasonic wedge bond to the surface of the chip. Okay, now these bonds are either being made at room temperature with ultrasonic vibration to scour off the surface oxides, or just squeezing that wire against the surface and pushing things aside. And the typical bond might look in the scanning electron microscope like that. This has actually got some corrosion on the bottom of it. Here's one where they didn't mechanically do that. They actually are using some scrubbing action here. They actually scrub the surface to get rid of some of the surface contaminants. This actually is a gold wire, if I remember. A gold ball bond, okay, where they actually used a little arc to melt the surface, and use the surface tension caused the ball to form, and then they push the ball into the surface, okay? And there are something like, I estimated, based on all the semiconductor chips that people make, and this is not the only way we bond, but something like 50 trillion of these welds made each year, on that order. So cold welding is important, but it's also important for other things. Somewhere here. Where did I put mine? Somewhere here in my mess. Oh, no, that's not it. I got it out this morning. I know I did. Unless it fell off. Well, in the meantime, I'll pass around. Here's some tungsten wire that is 15 microns in size, and you'll see a little, it's like very fine steel wool. I pulled it apart there. That actually is wire that's made for light bulbs, the filaments of light bulbs. And this is actually platinum wire, but the only place you're going to see this, it says start, it's got a little piece of tape here, it says start, and you can see one of the little wires, okay, at the end. Don't pull the platinum wire apart. The company that I'm doing the consulting for might want me to do something with that. I don't know.
I know you were a little fuzzy in the beginning of class with like the definitions of everything, but if you had to define what cold welding was in terms of like any types of parameters, is there any way to
cold
get
welding
more specific with
is
it?
something below, let's say, 300 degrees C. And the reason I'll say cold welding is below 300 C is because you can vaporize off moisture contamination. The weak van der Waals attraction contaminants will be vaporized off at above 300 degrees C or so, if I had to pick a temperature. There's no fixed temperature, but cold welding is where I'm doing nothing to really get rid of the contaminants other than just trying to push them aside with pressure. Okay, so I mean, obviously, cold welding with mercury would be, you know, you can come up with an exception for anything. But there are also things. There's a whole business down here in Attleboro, Massachusetts. A company called Texas Instruments has one of its facilities down here. They were in the late '80s. Were about to become a $1 billion company, just to that one facility in Attleboro, and they basically. It's called the Metals and Controls Division of Texas Instrument. Cecil Green, who was the founder of Texas Instruments, and the Green building here, the tallest building here at NDT with the radars on top and stuff. Cecil Green was in geology and geophysics and graduated in like 1927 or something. If you go up to the 3rd floor above my office, they'll say the Green Center of Physics. Anyway, he, as a geophysicist, went to the oil patch in Texas in the 1920s when he first graduated, and he bought a little company that made instruments for oil prospecting and stuff. And he called it Texas Instruments. Okay? And Texas Instruments didn't make semiconductors in 1930. Okay? They made bimetallic strips and little bored-on spiral gauges and stuff to measure pressure in the oil industry. And the thermostat over here has probably got a bimetallic strip. This is a bimetallic strip. And a bimetallic strip down here in Attleboro, they make tons and tons of material by roll bonding and cold welding. They also do warm welding, but roll welding together 2 sheets of material or multiple sheets of material. And why is it a control material? Because it doesn't matter which side you heat it, it always curls the same way. And that's how the thermostat in your house works. Okay, that's how the thermostat here works. Same way. It's just a bimetallic strip. 2 different metals, different coefficients of thermal expansion. See how smooth that is. When I was a student, the technician would do the glass blowing, and he'd always say, "Feel how smooth that is." After he'd done the blowing. Some students weren't too clever. But anyway. In any case, did that answer your question, John?
Yes, it did.
Okay. By the way, I got something for you up here.
Okay.
Okay. In any case, so there's the whole industry of roll bonding, making clad metals. There's a company that I work with down here that started in 1899 bonding gold to brass. And that's the reason why Attleboro, Massachusetts is called the gold capital of the world, is because they took the Sheffield process where people were putting sterling silver on brass to make sterling clad brass. But nowadays, because of what's now called Stearns Leach or something, Leach and Garner was what it was called in 1899. Leach and Garner basically was cladding gold to brass and making it into gold-filled material. So if you have jewelry or eyeglasses, in the old days, people used to like, yours might be precious metal, okay, but years ago we used to have precious metal eyeglasses. The price of gold's going up. Now we use titanium. I actually prefer titanium. It's better. But in the old days, 30 years ago, people used gold-filled materials so you can afford, 14-karat gold eyeglasses. But that's bonding of dissimilar materials by cold welding. Now, it's not cold welding, but there's another surface process, and that's friction welding, okay, where you squeeze 2 things together. I sent you a videotape of linear friction welding, and we'll talk about that in a second. This is rotational friction welding, where you basically take one bar that's stationary, another bar that's spinning on a machine that looks like a lathe, and you squeeze them together until they get hot, just like that videotape I sent you, the rubbing together the friction welding. That's actually a hot pressure weld. Now, in cold welding, you're basically going to be using pressure to deform the surface to push aside the surface contaminants. Okay? In friction welding or something, you're adding a little heat, frictional heat, to soften the material so it's easier to push it aside. But it's still a pressure welding process. It's not cold, but among the types of things that I'm looking at, getting down to how to get rid of the surface contamination and how do I get 100% area contact. I get 100% area contact by shearing those surfaces. It turns out, we might talk about it a little bit more, but we will talk about it a little bit more. Just squeezing 2 surfaces together will not give me 100% area contact. Shearing these mountain peaks against each other can give me 100% area contact. So in friction welding, or linear friction welding, I can spin it or I can rub it, and you can feel the frictional heat. Just rub your hands together and they'll get warm, right? So the frictional heat is shearing away the roughness, and then it's extruding out the contamination to get rid of the contamination, so I have a metal-metal bond. And that's how most of the universal joints on cars are made. Okay, they got to make the knuckle on the universal joint. You got a universal joint like this, right? And you got a big tubular shaft, and you got to weld this little forged or cast knuckle on the end. You know what I mean by the universal joint? The yoke, the Y-shaped yoke. So you take the Y-shaped piece, you keep it stationary, and you have a tube that comes in, and you just weld it to the back end of it. It makes the weld. You saw how fast those welds were made on the little video. It makes the weld in 1 or 2 seconds. If the process is working well, it works extremely well. Very, very reliable, as long as your parameters are right. Such that General Electric or Pratt & Whitney, they will take 2 turbine discs that are worth $30,000 a piece, and they will friction weld them together. Just spin one against the other in a circular friction weld and ram them together, then machine away the flash, and they've now made a $70,000 part. And if things are working well, you take 2 $30,000 parts and you make it into a $70,000 part. And if things aren't working well, you take 2 $30,000 parts and turn them into scrap. Okay? But if you have the right geometry, a circular geometry, you can make circular friction welds. For roll bonding, what you're trying to do is squeeze the surface and spread. You put 2 things together. It's just like making pie dough. You put one layer on top of another and you roll it out to try to stretch it out. And if you have too much loose flour on the surface, if anyone's ever rolled pie dough or cookie dough, if you got too much contaminant, dry flour, you got to roll it further to spread out the peanut butter, to spread out the surface to get down to the sticky surface that's going to stick together, okay? Same general principles as rolling pie dough. So now you know how to roll pie dough. Don't put too much flour on. And if you don't want it to stick to your board, you put flour on underneath. You contaminate it, right? To keep the pie dough from sticking to the table, right? So contaminant. This is not where the guy from General Electric, not General Electric, but General Motors learned about it. It was adhesive bonding when I talked about cleanliness, this next to godliness. And he realized that when you have this water jet cutting operation creating all kinds of contaminants, that's not a good place to be doing adhesive bonding right next to it. Okay? But not everybody can figure that out. So linear friction welding, well, I don't have an example of it to pass around, but there is a technology the Air Force has spent tens and tens of millions of dollars on called BLISK, okay, bladed disc. Bladed disc. And what they want to do is they want to take a disc that's going to go in a turbine engine, and they want to friction weld on all the blades. And why do you want to do that? Because you get rid of all these heavy flanges. Look at this blade. This part up here weighs almost nothing compared to this big Christmas tree structure down here, which is basically just a mechanical joint. That big mechanical joint requires the disc to have a huge flange to hold the high stresses as this thing slips in there, right? If you can get rid of all of that, you could take 20 pounds off a disc by getting rid of all those heavy flanges. So I could pass this one around. Actually, I might as well pass this one around. This one is actually a single crystal blade. If this blade, this is kind of from a 30-year-old type of aircraft. They get fancier now. If this was a new blade, it was good, it would be worth $4,000. And there's 100 of them on the disc. Okay. Now this one was grown as a single crystal. It's got a ceramic core, and it has all these turbulations inside because they blow air through it to cool it. Because the turbine operates, the melting temperature of this alloy is around 2,400 degrees Fahrenheit, and they run it in a gas at 3,000 degrees Fahrenheit. So if you lost your cooling air, you would melt your engine. Okay. Now they also have discs. This is a stator that have ceramic coatings on them, and it has a bunch of holes. These holes are actually laser or electron beam drilled. Some companies actually use electrical discharge machining, where you just plunge a wire into the surface and arc its way through. But you can see some of the holes on here. So the cooling gas comes up and out these holes to create a cold boundary layer of 1,000-degree Fahrenheit gas. Where do they get the high pressure 1,000-degree gas? Just bleed it off the compressor of the engine, okay? And they got plenty of 1,000-degree cooling air. And in fact, if they don't, the engine doesn't run anyway. So if you don't have compressor air, you don't have a running engine anyway. So it's a fairly reliable process. And that has allowed a substantial improvement in the efficiency of jet engines. In fact, that about 40 years ago, there was a big increase in efficiency, fuel efficiency, because of that. And every 50-degree higher temperature that you can operate an engine at is equivalent to about $2 billion a year in fuel savings for the airline industry. Okay, so a lot of money spent and by the Air Force and other people. Now, the Air Force is interested in making bladed discs because they can take 20 pounds off the turbine, which would be about 100 to 200 pounds off the engine. And if you can take 200 pounds off the engine, you can take about 2,000 pounds off the airframe, right? These are kind of a follow-on type of thing. And 2,000 pounds off the airframe either means greater range or greater payload, right?
10 more people. 10 more people there.
10 more people, well, if you're flying people around, but the Air Force only flies 1 or 2 people in a plane, right? Anyway, I remember I served on a committee for the Air Force that was the National Research Council that was looking at how the Air Force spends $300 million a year on their propulsion budget, research budget. And the goal, they had a couple of goals that I thought were interesting. One goal was they wanted to be able to have enough fuel efficiency so that a plane could take off anywhere in the world and land at the same base, go anywhere in the world. So they needed something that could go for 25,000 miles of distance. I said, well, why do you need that? You only need to go halfway around the world to get from one place. So they actually said they wanted to go. They figured we would never have any further bases anywhere else other than the continental United States places, and therefore they wanted to be able to take off and land at the same place and go anywhere in the world. Okay, so they needed an aircraft that could fly for 25,000 miles. Now, obviously, you guys, you float the ship around, right? And actually, this is a story that Mildred Firebaugh, after he ran the Seawolf program, he actually was Admiral Firebaugh, Chief Engineer of the Navy when the Seawolf had its problems. And in the 90s, but then later he retired and became a Vice President of Electric Boat. But I remember Mildred told me the story. He was at the Pentagon once, and the Air Force was complaining about the $15 billion price of a naval carrier. And Mildred said he just looked at them as they were making their pitch to the Secretary of Defense or whatever, and he says, well, you know, he had served in Vietnam, and he remembered they had not left a single aircraft carrier behind in Vietnam. Okay. So the Air Force has left, and their bases cost $15 billion too. Okay. And they do sometimes lose their overseas bases. Mount Pinatubo is one example, but there are other reasons, for political reasons, you lose a base. Now, your bases only last for 30 or 40 or 50 years, and then you scrap them. But nonetheless, you can move yours around, and you don't have to fly for 25,000 miles. The other goal they had is they wanted to develop an air-breathing engine that would travel at Mach 17. And I said, Mach 17, that's how fast the space shuttle goes. I mean, you're talking 10, 12,000 miles an hour. And I said, why do you want to do this in air? You're not going to be carrying people at that speed. And he said, no, this is to carry ordnance. And I said, well, why do you need it? I kept on pressing them. And they said, well, they once knew where Osama bin Laden was, but they had to get the ordnance there within 15 minutes.
Well, we had Project Global Strike, that would do it.
Let's go with laser web.
Global strike, oh wow, laser web. Okay, we can get into that, but that's another story. What's global strike?
You can use a submarine-launched ballistic missile with a conventional warhead
But not if you got to get inside Afghanistan in 15 minutes.
No, because you can launch it from pretty much anywhere you have a ballistic missile submarine that would touch it. The problem now is those missiles have nuclear warheads on them.
You can get into Afghanistan in 15 minutes?
That missile would easily make it into Afghanistan in 15 minutes if you launched it.
Oh, okay, we'll have to talk about this afterwards, okay? But I didn't know that you could do that. Look, I mean, there's lots of different solutions to the thing. I remember back in the days of the Alpha Sub, and the Navy was very concerned because the Alpha Sub could go faster underwater than our destroyers could go on top of the water. And so I was talking to one professor from Colorado School of Mines, and I said, well, it's a problem. And they also could dive deeper than the collapsed pressure of our depth charges, okay? And that wasn't a big problem. We just had never developed a depth charge. I mean, you could develop a depth charge and go deeper. You just had not done it because there wasn't a need to kill a whale, okay? Or whatever, it goes down that deep. In any case, and I said, well, that's a real problem if we can't, if they go faster, or we can't go below the collapse depth. He says, no, it just depends on the type of depth charge. Meaning, he says some depth charges you only have to get within a few miles.
Yeah.
So I guess I said, well, I guess if you're going to start shooting at their titanium submarines, you might as well start using all your ordnance. Anyway, that's another problem. So cold welding, the secret in cold welding of things is to use shear to create lots of new surface, okay? And the reason you have to have shear is if you just squeeze straight down on something like this, those asperities, even when you get to deforming the material, you'll still have some pores in there. You can prove that to yourself, and you should have a copy of this in your notes. Looking at the contact area during cold welding, macroscopically, we think of flat surfaces, and the area of contact is some area A, and we have a contact pressure, and if we go to the yield strength of the material, using the civil engineering definition here, the pressure is the yield is the force divided by the area of the flat surface. But microscopically, we have this rough area of contact. True area of contact is A sub T for true. Parent area, A sub A. And true area is much higher. But it turns out in a hardness test, because you have to flow the material on either side of that contact point, the contact pressure for yielding, the hardness is 3 times the yield strength of the material. Okay? If you're, even in a flat surface, if you're doing a hardness impression of something, in order, you have to deform all this material. You don't just deform the material directly underneath the punch. You have to extrude the material up and around. Okay? And people who study deformation and hardness and things, there's a rule of thumb in hardness testing that the hardness compressive strength that you measure is 3 times the compressive yield strength of a sample. If I was squeezing a sample of material between 2 punches like this, that's the volume of material I'd be deforming. But when I'm doing it on an infinite piece of material, I actually am deforming about 3 times as much material. And if you actually look at hardness indentation strengths, they're about 3 times the compressive yield strength of the material. Okay? Just because of the geometry effect. And so if I do that, you find that when you just squeeze these 2 guys together, you only get about 1/3 contact area. It's hard, you can squeeze until everything's just starting to flow, but you only, in just straight compressive yielding, you'll still have some voids in there. Okay? So that's a simple-minded way to think about it. The only way you can really get rid of those voids that are trapped in there is to shear the material. And that's what you're doing with the friction weld, right? You're getting rid of all the surface roughness and the contamination by just extruding the material out of there. Okay? Now, you can also use a soft material, and this graph should be in your notes. There's a book by, or paper, by Tilecoat in 1954 in the British Welding Journal, Investigations of Pressure Welding, And the key graph is this one right here, which like I say is in the handouts. The oxide to metal hardness versus the amount of deformation of the material. So if I'm going to try to roll coat some things, roll bond some things to make something like these bimetallic strips at Texas Instruments, they found, Tile Coat and others found that the amount of deformation is proportional to the oxide to metal hardness. Okay? Now the oxide is the contaminant on the surface, right? I got to get rid of that. And if I'm talking about a very soft material like indium, and it's got indium oxide, IN203, on the surface, indium oxide turns out to be a very hard ceramic material. Indium is softer than lead, okay? But I need to break up that oxide on the surface. I need to crack it and move it away. And the softer this is, the more it's just going to smear and fill in the cracks. The harder the oxide, the easier it is to break it up, to get a decent bond. And it turns out, by doing tests, indium has by far the highest oxide to metal hardness ratio, in part because it's such a soft metal, okay, but it also has an oxide that has the same crystal structure as aluminum. Aluminum has a very high hardness oxide. It's sapphire, okay, next to diamond on the Mohs scale of hardness. There's silicon carbide in between, but of naturally occurring materials like sapphire and diamond, aluminum is number 2 in the world after diamond in terms of hardness. Aluminum oxide is number 2 in hardness. And so, aluminum is a relatively soft metal. The big difference here is this is relatively pure aluminum. This is a higher strength aluminum alloy. And you have a big difference in how much deformation you have to have. Tin is in here. Tin's oxide is relatively smearable. It's like butter, okay, peanut butter. Spreads over the surface. Copper's even worse. Copper's got an oxide that smears over, like soft butter. Here's lead, iron, nickel. Most things take 80 to 90% creation of new surface in order to get a decent bond, because those oxides tend to spread out and smear over the surface. If you have a high hardness oxide that won't smear, then all you have to do is break it up, and you'll get the indium from the other side. Of course, you've got some indium here and some here, and this is indium oxide, this is indium up here, and you're trying to squeeze these together. And it turns out there's a paper that I'm not going to go through that actually just some guys out at Berkeley basically said, well, you just look at the statistics of how much new area you have on this and how much of that overlaps this other surface over here, and you can prove, actually I guess I can show it to you. I think it's on the back page of this. Here it is. It's just in your handout. Mohammed and Washburn, the Welding Journal in '75, and they look at the weld strength versus this solid state pressure welding, and the deformation ratio R. They come up with a formula which is just the statistics of creating these fractured regions, and what's the probability that one fractured region on one surface is going to match up with another fractured region, and they come up with a simple little formula that essentially matches the data very well for these things. So it turns out if I'm going to try to do cold welding, indium is the easiest material in the world. And back in the old days, and I mean really old days, not before I was born, but well before any of you were born, when they first made the first semiconductors, you'd have a little base, metal base with some ceramic feed-throughs, and you'd have one semiconductor in here, one transistor, inside a metal can. This is back right after the days of vacuum tubes. And the transistors, the silicon or germanium, were so delicate, and of course the single transistor you could actually see with your naked eye. I mean, these were huge transistors, right? But the can was a metal can, and basically they had an indium seal here. They wanted to cold weld it, and they would just squeeze the can, the top hat, onto the base with an indium seal. And essentially, you can call it a solder joint, but there's no flow of liquid. It was a cold weld of indium. And indium has essentially, a lot of indium alloys are being used today for solders, low temperature solders. But indium will cold weld much easier than anything else. 10% deformation because of the high oxide to metal hardness ratio. And that's how you get rid of the surface you don't get rid of the surface contamination. You just get, you may only get 10% bonded area, but 10% bonded area on a soft material like indium is like 100% strength, right? So far as that goes. So far as trying to make, we got to finish up here, but I'll show this last one. Another cold welding application is to weld wires together. This comes right out of the Welding Handbook, and it basically shows the dies to weld two aluminum wires together. So these are a wire here and a wire here, and the dies that grab it, and you kind of squeeze them, and you shear the material until you end up making it and then shearing off the joint. I think you got a copy of this. This I'll pass around next time. But this is a piece of tantalum wire welded that way, with the flash still on. Okay? Just squeeze it, you know, grab it again, squeeze it. If you look on the edges, you'll actually see where they grabbed it multiple times. And it's done right over here in Newton, Massachusetts. Okay? So I'll pass that around next time. Okay, so it's 9:20. We'll let you go.